Hello, welcome to another video lecture by Mr. Wolf. In this video I will look at a car going around in a circular motion. We will look at the physics behind this. This was part of a grant given to me by the BEF. So here we go with the physics behind a car in a circular path. Here we have a still photo of a car taking a turn. Now we're going to go through and break this down into a couple of different parts. So let's zoom in just a little bit. But before I do, I want to just go through a little bit of vector notation. A vector is a quantity, well that's a terrible arrow, is a quantity that has both magnitude and direction. There's an arrow. Now, when it's coming towards you, we use what's called an arrow notation to show that it's a circle, and that's not a circle, to show that it's a circle with a dot in the middle. This means that the arrow, it's the tip of the arrow coming towards you. Conversely, or inversely, if the arrow was going away from you, the vector or whatever quantity we're talking about, we would have an X representing the tail feathers of the arrow. So the top one here would show coming towards us. The bottom one would show going away from us. This is merely just to talk a little bit about vector notation. But let's go back to looking at our situation that we had with the car moving around a circular path. Alright, here we have the car coming towards us once again. And since it's coming towards us, we're going to say that the velocity is in our direction. Since the velocity is in our direction, I'm going to give it a vector arrow coming towards us and denote it with the vector v, or for velocity. So the car is traveling towards us. And what we've seen from the video before, it's accelerating, it's turning. Now, this acceleration is going to be directed towards the center of the path that it's following, towards the center of that circle. Acceleration is the change in the rate, the rate that velocity changes. So it's the change in velocity over time. And for a car traveling in a circular motion, or any object for that matter, the acceleration is always going to be directed towards the center of that circular path. So the acceleration is in this direction, towards the center of the circle. Now we need to take a moment and step back and look at what forces are causing this car to accelerate. In order to understand centripetal acceleration and circular motion better, we need to really look at the forces that are causing this to happen. And anytime that we want to look at the forces on an object, we need to really make a free body diagram. This is going to help us organize everything, separate things into X and Y variables if there's more than one dimension. And really, it's just good practice to kind of organize our thoughts. So we're going to start with a dot. And you can draw the dot in the center of your object, or it can just be on the side of your sheet of paper. But here we go, right in the center. There's my dot to indicate my object. Now, the first force that I have is the force of gravity. This is going to be acting downward. This is the weight of the object. We'll make it a little bit bigger. The force of gravity is acting downward. This here is the weight. Now, the second force that I'm going to look at is from the force on the car from the road. We know that there's a force on the car from the road by Newton's third law. The weight of the car is applying a force on the ground. The ground is applying a force back on the car. This force on the car from the ground is going to be the normal force. This force is going to act upward. And for objects at rest or most objects in situations, the normal force will often be equal to the weight. Not always though. So we need to pay attention to that. We know from before that this car is accelerating. So in order for it to be accelerating, there must be a net force, because net force depends on the mass is equal to the mass times the acceleration. The net force is also the sum of all the individual forces acting on an object. Right now, as I've drawn this free body diagram, the net force would be 0. This car is either at rest or moving at a constant velocity, not accelerating. We know this isn't true. We know there's some acceleration. So what could be causing the car to accelerate? A centripetal force is just any force that causes a car or an object to move in a circular path. The only other force acting on the car right now, well, there's going to be air resistance, but we're going to ignore that because air resistance is going to be in our third dimension of motion, actually going into the car. We're going to ignore air resistance. But the only other force acting on the car right now is the force of friction. And this is the force of friction, and it's going to be acting towards the center here. The force of friction is due to the force between the surface and the object, which is the normal force. In this case, we can actually zoom in here and we can look. We can see the tires contacting with the road, and this is providing a force that is going to be able to push the car inward. That's coming from the tires turning and actually directing some of the force from the contact point between the rubber and the tire and the actual road towards the center of the circular path. All right, what do we know so far? We're going to look at circular motion for this car. We know that acceleration is equal to a change in velocity over a period of time. We also know that a net force causes an object to accelerate. So net force is equal to mass times acceleration. The definition of a net force is the total forces on an object. So we calculate this by adding up the forces in individual directions. First the x, then the y, and finding the total or sum of forces on the object. Now, from our object from before, we know that we have our free body diagram where we have the weight of the object acting downward. We have the normal force of the object on the object from the road on the car acting upward, and we have the force of friction causing the acceleration and changing the direction. In a moment, I'll go through and I'll break down the derivation for how to actually find the acceleration of an object in traveling in a circular path. But right now I just want to give it to you, or show it to you, and go through it. So we have that an object moving in a circular path accelerates, and this depends on its velocity, but really it's the speed squared divided by the radius of the circular path. These combine together to give us the centripetal force. Again, it's not a new force. It's just it's the net force acting on an object. But we give it this name of anything centripetal, meaning center seeking, and it is a force that causes an object to move around in a circular path. So Fc is really mass times A sub c. This is, again, it's not a new force. It is just any force that exists that causes an object to move around in a circular path. So here I have my car moving at some velocity on... So here I have my car traveling around a circular path at some velocity v. The circular path has radius r. At some point later on, it will be moving with velocity v along the circular path like this. So at some later point, it's moving with velocity v now drawn in purple, along the same radial path, along the circular path at the same radius from the center of the circle. We can look at a couple of different parts from this. We know that the change in position from where it initially was to where it is now along the circular path follows some angle theta. We can use this approximation and take the initial velocity that it had and combine it with the final velocity that it has to look at the change in velocity. If I take the final velocity and I move it back, that vector, and I line it up along from that line back by the initial velocity, I can create a triangle going down, and we know that this angle is 90 degrees because this angle up here was 90 degrees. Because of that, I can use the relationship between two triangles and show that this angle in here is the same as theta. Let me draw this for us. From this, the initial red velocity and the final purple velocity, I can look at the change in velocity along here. This here represents the change in velocity. And there's a relationship between the angle that the angle theta and the change in velocity and the initial velocity as well. So now I've drawn this with the change in position from point A to point B. I finally labeled them. Sorry about not doing that before. And it's along the same angle, same radial distance as the initial triangle. I can look at this and say, well, the distance is equal to the speed, because we're only looking at we're going to assume our conditions here of constant speed, but it's changing direction. I can assume that the speed is equal to the distance is equal to the speed multiplied by the change in time. Like so. From here, I can set it as a limit as the change in time goes to 0. So I can rearrange this formula here. Since these two triangles both have the same apex angle, I can make an assumption relating the theta for both triangles are speed times the change in time, the initial velocity, and the change in velocity, so that I can compare these two triangles. I can rearrange this so that I now have, let me get a nice pretty color here for this. Stick with the pink. I can rearrange this to say that v squared over r is equal to a change in velocity over time. We know that a change in velocity over a time is merely an acceleration. So here I've gone through a proof to show that, and I mean I've kind of skipped some steps here in showing some limits and stuff, but and really if you want to look at it, we can do out the calculus some other time. But I've shown that centripetal acceleration is a velocity, depends on the speed squared divided by the radius of the circular path. Awesome.